Welcome to Mrs. Lee's Chemistry Academy, where no students are left behind. Today we're going to talk about part 3 of gas laws on gas density, molar mass, and Dalton's law. Tying to the learning objectives from College Board, the student can apply mathematical relationships or estimation to determine macroscopic variables for ideal gases. That the student is able to relate quantities, either measured mass of substances, volume of solutions, or volume and pressure of gases, to identify stoichiometric relationship for a reaction, including situations involving limiting reactant. Now, I would like to show you how we can derive a formula to determine gas density and molar mass. So we start off with the ideal gas law. PV is equal to nRT. Now we can replace the number of moles N by replacing it with mass over molar mass, or M over MM. Now we also divide both sides by V, the volume, and now we have also replacing the M over V by density, and cancellating out the V on the left-hand side. So we are now left with P is equal to dRT over mm, or pressure is density times ideal gas constant times temperature over molar mass, or molar mass is dRT over P, and I joke around with my kids saying molar mass is dirt over P. Mole fraction. In a mixture of ideal gases, the molecules do not exert intermolecular force on each other. Therefore, they act independently of one another. The partial pressure of each gas is equal to the mole fraction of that gas times total pressure. So for partial pressure of A, it is equal to the mole fraction of A times total pressure P sub T, which is equal to the moles of A over moles total times total pressure, where the P sub A represents partial pressure of A, and chi of A represents mole fraction of A, and P sub T meaning the total pressure of the system. Dalton's law of partial pressure, which states the sum of partial pressure of all components in a mixture of gases equals the total pressure. In other words, if you have A, B, and C types of gas molecules as a mixture in the container, the total pressure will be the partial pressure of A plus that of B plus that of C. Now, here is a diagram showing a container containing half a mole of nitrogen at 1 atmospheric pressure. And the same container is now replaced by 1.5 moles of argon, which exerts a pressure of 3 atm. If we mix the nitrogen and the argon together, now we have half a mole of N2 and 1.5 mole of argon. The total pressure is 4 atm, which is 1 plus 3 equal to 4 atm. Practice problem number 1. A gas mixture has 1.85 grams of nitrogen and 0.49 grams of hydrogen in a 2.5 liter flask at 25 degrees C. Calculate the partial pressure of each gas in the flask. Calculate the density of the mixture. And if the mixture combines to form ammonia, give the mole fraction of all species present at the end of the reaction. First, we calculate moles of nitrogen. Take the 2.35 grams divided by the molar mass. We have 0.0839 moles of nitrogen. Now we calculate moles of hydrogen. Take the 0.490 gram divided by molar mass of hydrogen. We get 0.243 moles of hydrogen. Now to calculate the total pressure, we add up the two types of moles of nitrogen and hydrogen times ideal gas constant times temperature over the volume. We have 3.20 atm. Therefore, the partial pressure of nitrogen is the mole fraction of nitrogen times total pressure, which is 0.0839 mole over total 0.327 moles times the pressure of 3.20 atm equal to 0.821 atm. And similarly, the partial pressure of hydrogen is calculated in a similar fashion by using 0.243 moles of hydrogen as its individual mole component, yielding 2.38 atm. Now the density, when we have a mixture, we can add up the total mass over the total volume, and now we have 1.14 gram per liter. Okay, here now we come to the last question, which deals with how much of the species are present in terms of mole fraction. So I write the equation first, 3 moles of hydrogen combining with 1 mole of N2 to make 2 moles of ammonia. Now I like to use something called the ICE table. I standing for initial. So initially I have 0.243 moles of hydrogen, 0.0839 moles of nitrogen. And I have determined that the hydrogen is the limiting reactant, therefore the nitrogen is the excess reactant having leftovers. Now C representing change. All that hydrogen will be used up, but the nitrogen will use up 1/3 of the moles of hydrogen. And the ammonia form will be 2/3 of the moles of hydrogen, 2/3. And therefore now, we come to the end, we have nothing of hydrogen left. We have 0.0029 moles of nitrogen, and we have 0.162 moles of ammonia. So the total moles remaining is equal to the moles of nitrogen and the moles of ammonia, which is 0.165 moles. And when we determine the mole fraction of nitrogen, that turns out to be 0.018, and the mole fraction of ammonia turns out to be 0.982. Here is a diagram showing how we collect gas over water. Now here I have a test tube of hydrochloric acid reacting with the zinc, generating hydrogen gas. And that's bubbled into a container that has been fully filled with water but inverted upside down into a water bath. So as the hydrogen gas bubbles in, the water will come out and being displaced. When we measure the pressure, it is important that we equalize the internal water level with the external water level. Externally, it represents the pressure from the air, and internally because we collect the gas over water. So that's not only just the dry gas alone, we also have the water vapor present. So inside the container, there are 2 kinds of gases, the gas and the water vapor. When we equalize the water levels, we are equalizing the pressure. So the total pressure is equal to pressure of gas and that of water vapor. So this slide here just basically reiterates what I said earlier, the importance of considering the vapor pressure of water at a particular temperature. And we can determine that from a table. Vapor pressure remains constant at a particular temperature. Practice problem number 2. Molar mass of butane. Design an experiment to determine the molar mass of butane gas. Construct a table to collect data. Calculate molar mass of butane and determine percent error. And then explain whether the molar mass will increase or decrease if the butane lighter was not dried when it was remassed, and the water column inside the graduated cylinder is taller than the outside water level in the water bath. So I'd like to draw the picture. Here I have this graduated cylinder that's fully filled with water and turned upside down and immersed into a water bath. So initially there's water in the water bath, and this graduated cylinder is fully filled. Now I have my butane lighter, which I have removed the cap and I masked it before. Then now I put my butane lighter here, assuming I'm holding it, to release the butane gas. So as the bubble goes in, the water comes out. So initially there's a lot of water. Let's say the water gradually is being displaced by the gas. And so now the important thing is to equalize the water levels in the graduated cylinder and externally, by making sure that these levels are equal before we take a reading. Because as you know, externally we have the air pressure, and internally we have that of the water vapor and that of the butane gas, C4H10. Okay. Now the design, first we mask the lighter, and then we fill a 250 milliliter graduated cylinder with water up to the rim, covered with a watch glass, carefully inverted upside down in the water bath. Make sure there's no air bubbles. Record the temperature of the water bath and the air pressure as well. Place the lighter beneath the graduated cylinder, release the butane into the cylinder. Collect about 150 milliliter of the butane gas in the cylinder by water displacement. Then dry the butane lighter thoroughly and mask it again. The data. Atmospheric pressure 101.14 kilopascal. Water temperature 25 degrees C. Vapor pressure water 23.76 millimeter mercury. Butane lighter initially weighted 12.1438 grams. And then final mass is 11.8615 grams. Make sure that your butane lighter is not wet, very important. And so the mass of butane released is the difference between the two numbers, 0.2823 grams. And the volume of the gas from the graduated cylinder, 145 milliliter. Now we can do all the calculations. First, we find the pressure of butane by taking the atmospheric pressure, converting into millimeter mercury, and subtracting the water vapor pressure from it, and we have 735 millimeter mercury. Now we calculate moles of butane using ideal gas law, and we find it to be 0.00573 moles. Now we determine the molar mass. We take the mass of the butane released divided by the moles. We have 49.3 grams per mole. And now we compare it to the theoretical value of 58.12 grams per mole, and we have a 15.2% error. If the butane lighter was wet with water, the mass of the butane gas released would appear to be smaller because we did it by subtraction, and therefore resulting in a smaller calculated molar mass. If the water column inside the graduated cylinder is taller than the external water level, that means a smaller volume of butane gas would be measured, therefore resulting in a smaller calculated moles of butane released and a larger calculated molar mass. Practice problem number 3. Determine the molar volume of a gas. Student wanted to determine the molar volume of hydrogen and STP. He reacted the strips of magnesium ribbon with excessive hydrochloric acid, and it was the hydrogen gas was collected by water displacement in an inverted bottle. The following data was obtained. Mass of ribbon 0.0239 grams. Volume of gas collected over water 25.8 milliliter. Water temperature 24.0 degrees C. Atmospheric pressure 755 millimeter mercury. Water vapor, read from a table, 23.78 millimeter mercury. Now use the above data to calculate the molar volume of hydrogen at STP. Determine the percent error, and will the calculated molar volume be too large or too small? If the vapor pressure of water is not accounted for, explain it. So here's a diagram of the magnesium ribbon in hydrochloric acid generating hydrogen gas collected by water displacement, and also the net ionic equation of magnesium plus 2H plus, meaning that from the hydrochloric acid, to yield Mg2 plus, meaning magnesium chloride and hydrogen gas. Now here is practice problem number 3. Calculations. The moles of magnesium is calculated by dividing the mass by the molar mass of magnesium, which turns out to be 9.83 times 10 to the power negative 4 moles. Now from the balance equation, 1 mole of magnesium yields 1 mole of hydrogen. Therefore, the moles of hydrogen will be the same, which is also 9.83 times 10 to the negative 4 moles. Remembering, we have to account for the vapor pressure of water, so we need to subtract that from the air pressure, which is equal now to the pressure of the hydrogen, which comes out to be 731 millimeter mercury. Now we need to convert it to standard temperature and pressure conditions. We will use the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. So the volume is what we are looking for, and it turns out to be 22.8 milliliter or 0.0228 liters. Therefore, the molar volume of hydrogen at STP is calculated by dividing the volume by the mole, which turns out to be 23.2 liters per mole. Compared to 22.4 liters per mole, the percent error is 3.57%. Now, if we did not account for water vapor, what would happen? That means the partial pressure of hydrogen would have been larger than it's supposed to be, resulted into a greater calculated molar volume. So to sum up what we have learned today in this lesson, first we learned the mathematical relationship between density and molar mass, and remember how I derived the formula. 2, we learned the Dalton's law of partial pressure, that the total pressure is equal to the sum of the individual components' partial pressure. And we learned how to collect gas by water displacement, and that we need to account for the water vapor pressure at that temperature. We further did data analysis of molar volume of a gas using that experiment, and we also designed the experiment and performed the data analysis of molar mass of butane. I hope that the above lesson has been helpful to you. I welcome any comments from you, and I hope to see you again next time.